Hello class, welcome back to our physical sciences lessons. Today we are going to continue looking at work, energy and power, and we are going to specifically look at the work-energy theorem. Now before we go any further, again we have a look at our exam guidelines. The first thing is that we need to be able to state the work-energy theorem. That's the definition there. Going to have a look at that in a moment, and then also be able to apply the work-energy theorem to objects on horizontal, vertical and inclined planes for both frictionless and rough surfaces. But let's get back to our work-energy theorem. So we start as always with the definition. Remember the THM dot, that's just a little abbreviation for theorem. Shouldn't be too strange. Now what is the work-energy theorem? We've mentioned this or alluded to it in the previous lesson. We simply say that the work done on an object by a net force is equal to the change in the object's kinetic energy. Now, if we've been reading a bit more this lockdown as we're supposed to, then maybe we are a little bit more comfortable with definitions, but either way, these definitions always become a little bit simpler or clearer when we put in an equation. The equation simply says that the net work is equal to the change in my kinetic energy. Delta EK means the change in kinetic energy. Alright, now we can express this in just another way. We can also say that this is equal to my EK final minus my EK initial. Now, what is this net work or work net? This is, of course, the work done, like we've looked at in the previous section, by the net force. And we know that the net force is a single force that has the same effect as all of my forces acting on my object combined. So if we look at the net work done on an object, it's either, we could think of it two ways, either the sum of all of the work of the various forces acting on the object, or we could just find the F net and then find the work done by that net force. Same thing here. So what we're going to do is we're going to look at an example firstly. Now let's consider, like we did in the previous section, a block. I've got a block and we are exerting a force of 10 newtons on this block, and we're going to just put our displacement over there. We're going to say that my displacement is equal to 6 meters, and we say that the angle between the net force, or rather this applied force, and my displacement is going to be 30 degrees. Now, just to make this a little bit more familiar, we're just going to indicate the mass here. It's not really necessary for us, but we are also going to include a kinetic friction. We're going to say this is Fk equals, let's say 3 newtons. So the question here that I want us to see if we can answer is that if the block starts from rest, determine its final kinetic energy. Alright, so we have a couple of forces acting on the block that is shown. Of course, we also have some forces that we know are acting on the block that are not shown. For instance, we know that I've got my Fg acting downwards, and I will also have a normal force acting upwards. Now, let's consider here what my net force is going to be. Well, my frictional force is obviously towards the left. My applied force is towards the right, but it's also up at an angle of 30 degrees. So what that means is some of my applied force is towards the right, whilst another amount is going to be vertically upwards. The object is, we assume that it's moving towards the right or accelerating towards the right, because that 10 newtons is obviously much larger than my 3 newtons, even though it's at an angle. But the vertical components are going to give me a net force of 0 because this object is lying on a table, so it's actually remaining stationary. It's not accelerating upwards or downwards like we've seen before. So we are only, with the net force, we are only interested in the force towards the right and the force towards the left, so in my horizontal components. So I want to find this final kinetic energy, so that's my EKF. I know that I see there's my EKF, so in order to find my EKF, I'm going to need to know what my initial kinetic energy is going to be, as well as the net work that's done on the object. Kinetic energy, or my initial kinetic energy, that's easy because they tell us that the block starts from rest. Over the work net, that's going to be what I need to calculate. Now, like I said, that net work, of course, that is the work done by my net force. So that's where we're going to start. We're going to see what my net force is going to be equal to. Like I said, we ignore the vertical component because it's going to cancel. Well, the net force vertically is going to be 0. So I'm only interested in what's happening horizontally for the time being. So I say the horizontal net force is going to be F applied X. That is the horizontal component of this applied force of that 10 newtons, plus the Fk. Now I'm just saying plus here. I know that the one's going to be positive, the other one's going to be negative. We are going to most likely choose right as positive. So we say then my applied force, its X component, like we always do, we're going to use my cos. So I say 10 times cos of 30 degrees. Then I subtract from that my 3 newtons, because like I said, we're choosing right as positive and left as negative. We put that into our calculator, where we say 10 times cos of 30 degrees, and that gives me 8,66 and minus the 3, so that gives me a final answer of 5,66 newtons. Alright, that's towards the right. So now we've got my net force. We know that it's going to be 5,66 newtons. So all of these forces acting on the object, I can simply distill them down, and I know that all of them are going to have the same effect as a net force, or a single force of 5,66 newtons towards the right. So I go on now. Now I want to calculate the net force, or rather the net work. So I say W net is equal to F net delta X cos theta. Like we've done in the previous section, work equals force times displacement times cos of the angle between those two. Now, the net force, we've calculated that as 5,66. But then my displacement, we said that it's 6 meters. And now we need cos of the angle between my displacement, which is delta x, and my net force. But my net force, we said it's going to be in the x direction. So the angle here is not going to be 30 degrees because it's not, my net force isn't upwards at 30 degrees, it's horizontal. All right, remember my force of gravity combined with my normal force, that's going to, if I add the y component of that 10 newtons, that's going to give me 0. So I'm only interested in that x component. So the angle here, they are parallel to each other, so the angle is going to be 0 degrees. I just multiply with my 5,66 with 6. I go back quickly. Where was it? Where we're now 10 times cos 30 minus 3. Just want to use our calculator value, and I multiply that with 6, and that gives me an answer of 33,96 joules. Right, we're not finished because again we want that final kinetic energy. So I say, well, according to the work-energy theorem, the net work is equal to the change in kinetic energy, which we said is Ek final minus Ek initial. So we say, therefore, 33,96 is equal to my EKF minus 0. Again, because the block starts from rest, that means that my initial kinetic energy is going to be 0. So we can see here that my EKF is equal to 33.96 joules. Now, if we have our kinetic energy, and in this case we have our mass, in this question they could also ask us, for instance, what my final velocity would be. And then I would just use this EKF equals a half mv f squared. So we can see this work-energy theorem actually allows us to go from a distance and a force, or displacement and a force applied, to actually calculating what my final velocity or even initial velocity would be. All right, speaking of which, let's have a look at our second example. Now, this one is taken again from our Siavula textbook. All right, example 2, this is the worked example 7 on page 233 of the Siavula textbook. It tells us that the driver of a 1,000 kilogram car traveling at a speed of 16.7 meters per second applies the car's brakes when he sees a red light. The car's brake provide a frictional force of 8,000 newtons. Determine the stopping distance of the car. Alright, so like we often do in this case, it's helpful for us to list some of the quantities that we know. We know that the mass of the car or the object is 1,000 kilograms. The initial velocity is 16.7 meters per second. And then also we can see that there is a final velocity of 0 meters per second. Now, why am I talking about velocities? Because remember, we are going to be using this theorem here. The net work done on the object, we know what the net force is. It's the 8,000 newtons. All right. And we know that that's equal to my change in kinetic energy, which is equal to the final kinetic energy minus the initial kinetic energy. So if I can find that my final kinetic energy and my initial kinetic energy, I can find what my net work is, and then again we'll use the equation for work. So let's get started. Let's list our values that we have. We know that the VF is going to be 0 meters per second because they say it's going to we're interested in the stopping distance. Stopping means my velocity is equal to 0. My initial velocity, that's going to be 16.7 meters per second. That's also given. And then the mass is 1,000 kilograms. So first things first, we know that we're going to be working with the work-energy theorems. And in order to find that, or to find my distance, I first need my change in kinetic energy. Now my change in kinetic energy, that's going to be EKF minus EKI. What is my EKF? I can say that's going to be 0 immediately because my final velocity is going to be 0. It's coming to a rest, so the kinetic energy means, or coming to rest means, of course, my velocity and my kinetic energy is going to be 0. Then I say minus a half times mvf squared. I substitute in my values. My mass is going to be 1,000, and my final, or rather my initial velocity, my initial velocity is going to be 16.7. And remember the square, that's where we're likely to make our mistakes. So we say 0.5 times 1,000 times 16.7 squared. And that gives me a negative answer of 139,445 joules. Now we can, why is it significant that we have a negative answer there? Well, in this case, the object, or the car is moving forwards. Braking always works in the opposite direction of the motion. It's going to slow down the car. So the work done by that by the brakes must be negative as well, and the change in kinetic energy is going to be negative as well because it's decreasing. My kinetic energy is going is decreasing. It's becoming less. So next we now use my net work, which is equal to my change in kinetic energy. I also know that that net work is going to be equal to F net delta x cos theta, and that's still equal to change in kinetic energy. And now I start substituting in. We assume the only force here, that's given to us is the net force. Of course, there will be the downwards force of, let's just draw this quickly here. I'm going to have my displacement in this direction that's unknown, but I know it's going to be forwards. I've got my Fg downwards, I've got my normal force upwards, and then I've got my force, let's call it my net force or my braking force towards the left. Normal force and force of gravity, those are going to, when added up, give me a net force of 0. So the only force is going to be my braking force. That's going to be equal to my net force. And that net force is 8,000 newtons. So I substitute that in, 8,000 times the displacement, which is the one that I want to find. And now, cos theta, the angle is going to be 180, because that's the angle between my displacement, which is forwards, and my braking force, which is opposing that motion, which is going to be backwards. So I say that angle is going to be 180 degrees. And that gives me an answer of negative 139,445. And we can see that cos 180 degrees, that's going to be a -1, so it will cancel out with that negative answer, so that I find a positive displacement. And that makes sense, because I'm going to be moving forwards. I've got an initial velocity, I'm applying brakes, the car is going to be moving forward for a while until it comes to a stop. So I say, very simply here, delta x is equal to my negative 139,445 divided by negative 8,000. That negative, remember, comes from the cos cos 180 degrees. And that gives me a final answer of 17,4 meters. And we are going to say, this is where they are asking us for the stopping distance. So I don't need to say forwards. I can just say right down here at the bottom, stopping distance. Distance, of course, being a scalar, is just 17,4 meters. All right, that's all for work energy theorem at the moment. In the next lesson, we'll be having a look at those conservative and non-conservative forces, and then we'll jump into some more exercises and problem solving. Goodbye.